my opponent. Okay. So I'm going to briefly introduce Michael, and also I'm actually joined by my colleagues. So Isong and Joel and Sergio, and I think it's almost like a family. Isong has been working very closely with Michael. And for duration of his PhD working on learning based control, and also studying with this region project with Joel. So yes, so these are not strangers to this research. And Mike actually did his undergraduate degree in Illinois, and also faculty member again. So I was his academic coach when he was a freshman. So it means a lot. He talks a lot about not me, right? How nice person I am. Not that. It means a lot, talking a lot about Michael. How patient. Almost 10 years I've been working on fascinating research projects. So I think the privilege of faculty is really seeing your students grow intellectually and then prosper. So I'm really proud of Michael. And just so you know, Michael will get a job, actually letting our job. And he's going to be in the future leaders program of nursing program. So basically a special elite program producing next leaders of nursing. Right. So Michael, with that, over to you.
All right, thank you, Sunjo. Very kind, and thank you to the committee for taking the time to do the examination, and for everyone for showing up. This is a great turnout. I'm really excited to tell you about my research. So I titled my thesis a little bit vaguely, Methods for Learning-Based Control. And I definitely spent a lot of time thinking about that, and that wasn't the last thing I did on my thesis document. So here we go. Growing applications for uninhabited aerial vehicles. So today we're seeing a lot of different uses for UAVs kind of emerging and gaining some traction and definitely a lot of interest. One really big one that could like totally change the way cities look is this idea of urban air mobility. So I have this image from NASA, and NASA and the FAA are looking a lot into this and how to regulate it, right? But just you know, basically aerial roads through cities and how to do that safely and without disturbing society, right? And then there's a whole plethora of companies coming up with concept vehicles for urban air mobility. We see UAVs used a lot, especially in our lab, in scientific applications. So these two photos are courtesy of Matt Anderson and the rest of the lab group, right? So here's one drone that we fly. It's a hexarotor that we use to navigate rivers, and then another radar testbed. And then another common use for UAVs is this idea of last mile delivery, right? So the Google Wing project is one emerging thing, and then we also have Amazon with their package delivery drone, with the idea that, you know, it can deliver things on demand very quickly. So this is quite challenging, though. There's a reason that there's a lot of interest, but not as much application yet in society, and it's more than just regulation, right? One challenge of UAVs is that we have to be robust to a whole bunch of different conditions. So here you can see one of our drones flying in the real weather wind tunnel upstairs here at Caltech. You can see the smoke being generated and kind of flowing past the drone. And this is, I think, the easiest case for flying in wind, right? It's uniform, it's controlled. When you get to this urban environment, this is an open access image that I pulled from the internet, right? Showing if you have two buildings with wind flowing over it, right, you can get really complex airflow between the buildings. And that is a challenge, to say the least, for vehicles flying in those conditions. We also see, like on our lab vehicles, we're very quickly changing the configuration. So for example, on both of these drones, you can see that radar testbed. Here, it's a large wing-like surface pretty far out from the center of mass, right? That creates a lot of moment and force on the vehicle. Here, it's sitting right underneath the propellers. So it's getting all the downwash, and these are angled surfaces. And then here you can see, this is maybe the more benign case, which is where we just have a camera payload, and that's just changing the center of mass of the vehicle. And then when we look at something like urban air mobility, right? These are small, lightweight vehicles, and then you throw passengers in there and their mass changes by, I don't know, 10, 20%, right? Changing center of gravity, passengers move around. It's challenging to say the least. Right, and then we can look at fault tolerant control applications, right? So I just put one up here. Right, if we're going to have UAVs that are everywhere in society, we need them to be really robust, right, and capable of doing this emergency landing on their own. Right, when something goes wrong, they need to have their bailout so that they don't harm people that they're near. So how are we going to solve these problems? Machine learning. Right, so we are in 2023, so this is the approach we'll be taking. But I'm going to put a little asterisk by it. And right, most of the presentation will be focused on this asterisk and how we make sure that this is done safely and robustly. So what are the challenges to applying machine learning on a real system? Well, first, like we've talked about, we have complex and changing uncertainty, right? We're in challenging environments. So again, this is the real weather wind tunnel with our drone flying. Here we were just flying it through some race gates, right? We have these nice propeller guards. It's a soft surface if you hit it, but that's not always the case, right? That's just our lab environment. We need to look at things that are computationally efficient. So we run all of our algorithms on this Raspberry Pi. So this is actually mounted right on top of this drone. We run everything on board, and we're trying to use readily available hardware and kind of standard compute power. And then, like I've discussed, right, we need these safety critical applications. We need to have not only a guarantee that they'll perform well in their design condition, but they need to fail gracefully when we go outside of our kind of intended operating point. All right, so how do we address these challenges? So this is the outline for the talk. We're going to start by talking about Neural Lander. This is a paper with Guanya Shi and Zichen Shi as co-first authors with me. It was in 2019, and we submitted it to ICRA, the International Conference on Robotics and Autonomy. And what we address here are, like I said, right, the fundamentals of residual learning based control, right? What are some key considerations that all of the frameworks will have? And that'll kind of lay the basis for the rest of the talk. Next, I'll talk about NeuralFly. Some of you might remember I gave a talk here almost exactly a year ago, focused on this paper. So we'll talk about it more today and how we can use learning to adapt to different changing environments. Next, I'll talk about some extensions that we're working on to handle fault-tolerant control scenarios. So we're working with this octarotor. We have 8 propellers, and we want to be able to handle a propeller going out or multiple propellers going out and losing some control of the vehicle. And finally, I'll talk a little bit about some work on delay compensation. And this is addressing something that we intentionally set up to be orthogonal to the Neural Lander and NeuralFly framework, right? How do you handle time delays in your system? All right, so let's get into it. So the first thing I'm going to do here is show the first equation, right? So let's look at the kind of simplest breakdown of the dynamics that we can, right? And so if you look at just the black text here, x dot equals f of x and u, right? X is our state, f is our known dynamics model, x dot is how the vehicle changes in time, and then u is the thing we control. So what we're really trying to do in Neural Lander, and really in all of this work, is we're trying to learn some additional term on top of the known model, right? Where this is some unknown part of the dynamics model. And we're trying to see, how to incorporate that into the control system. Right, so this first chapter, Neural Lander, right? We were using this Intel Aerodrone. This was early in my PhD, so I was not as good at taking pictures. So this is a stock image. We'll have fewer stock images as we go on. Right, okay, so Neural Lander, right? We can guess neural network, Lander, we're landing, right? So you saw that GIF, and what we're trying to do is predict ground effects for the quadrotor drone. So the way that we do this, right, we have, I moved a few things around, but still the same basic dynamics from earlier, right? X dot, some known model. This BU says that we have some knowledge of how the system or our control action affects the system. And then we're gonna try to learn this G component using, in our case, a neural network, but really any black box model. So like I just said, right, we're gonna approximate this G as a deep neural network. And then we have this kind of conventional control design where we invert the control behavior of the system. We have some stabilizing terms. We cancel out the known model. And then really the key piece here is we're doing what's kind of like a feedback linearization approach on the learned dynamics. But there are a few challenges that this poses. And the first thing I'm going to point out is that if you ignore this orange G term, right, the control input is on the left-hand side. So it's kind of easy to figure out what it is, right? We have like a closed form explicit solution for a control input. But now by putting it in the neural network, we suddenly made this problem a lot more hard to solve, especially when you have to do it very quickly. So the solution that we came up with was to use this fixed point iteration scheme, where we use the control input at the last time step to approximate the neural network. There are some challenges with this, which is really what NeuralLander is focused on solving, right? And so the kind of key condition that came out of the paper, right, is this kind of mathy looking equation, but essentially we have the maximum singular value of the inverse, right? So this is how quickly the dynamics change according to our known model, or sorry, the fixed point iteration changes according to our known model. And then we have the Lipschitz constant of that neural network. And so by writing this condition, right, the maximum singular value of the inverse D matrix times the Lipschitz constant of the neural network has to be less than 1. What we're saying is that, well, first, that's going to guarantee that this fixed point iteration converges, right? And we have a control solution, so we haven't set up an impossible problem for ourselves. Right, secondly, this is going to guarantee or help us guarantee the performance of the system. Right, and we guarantee performance by looking at this Lyapunov-like stability analysis, right? So you take some Lyapunov function, right? It looks a little bit easier here because I've simplified the equations for the presentation. But really the key result is that the error in our state or tracking, so the performance of the system, is bounded by the maximum difference between the true dynamics and the learned dynamics, right? So that's kind of the key result, that graceful failure that I talked about earlier. And all of our frameworks we're striving to kind of get this type of result. And then you see on the bottom, K is the control gain. And then we have this Lipschitz constant times rho. And this is essentially saying that we're penalized by that neural network converging slow, or sorry, the fixed point iteration converging slowly will penalize us. So rho is a constant that is essentially how fast this fixed point iteration converge. So what are the key takeaways from NeuralLander? First, spectral normalization, it's a great thing, right? And here it really helps us guarantee stability. Second, we can treat the, right, we set up a really hard problem for ourselves to solve by putting the control input into the neural network, but we can use fixed point iteration to overcome that challenge. And then thirdly, right, in this framework, we can get this nice kind of graceful failure result. All right, so I'm going to go on and show a quick video here. So this is a sped up video. We're flying the drone over this table, as you can see. On the top, we're running our NeuralLander, right, learning-based control scheme. On the bottom is the baseline controller. And even though NeuralLander is flying much closer to the table, you can see that the baseline method, every time it goes over the edge of the table, oh, we just lost the video. Every time it goes over the edge of the table, it is, okay, I'm not gonna worry about it. It's affected by the so-called ground effect of the table, and it kind of like bounces up as it hits the table. Right, so the neural network does something and we're able to compensate for those dynamics, which is cool. Why does that work? I talked a little bit about spectral normalization earlier, right? And it not only helps the control scheme and allows us to get those guarantees, but it also improves the learning performance. So if we look at this graph here, or these two plots here, it's two heat maps with and without spectral normalization. So you can see on the right side of each plot, this is where our training data was. And then on the left side, to the left of this green line where it says new domain, right, that's outside the training domain. And you see the color represents that buoyancy force that you get as you're close to the ground. So the height on the graph is how far you are from the ground. And then left, right is the speed that you're approaching the ground at. And you can see that in our training domain, right, we get this buoyancy effect near the ground. But then as soon as we look at a neural network prediction outside of the training domain, right, we get this kind of black color, right, which indicates a suction effect, something that is sort of non-physical and we don't really expect to happen, right? We expect similar behavior with slightly changing velocity. When we add in spectral normalization, right, we see a nice, smooth, expectable behavior. Okay, so maybe you don't know a lot about ground effect, so you're not totally convinced. Let me show you the table result. So now on this figure, I've changed my axes. The left, right on this figure is, or left, right, and up and down are both horizontal movement, right? It's the X and Y plane just above the table. And you can see that with spectral normalization, right, we get a consistent ground effect prediction across the whole surface of the table, which I think is realistic to expect. Without spectral normalization, right, we had pretty sparse data. I don't remember exactly for this one because it was a while ago, but it was around 10 minutes of flight data that we used, right? So we probably didn't fly the drone at the perfect condition to tell the neural network what the ground effect was right here. So without spectral normalization, right, we see just kind of unrealistic dynamics. Okay, so what are the takeaways from neural lander? First, spectral normalization, it's key in the stability proof, but also it's become really popular recently in machine learning because of these robustness guarantees. Second, we can handle the non-affine control problem using fixed point iteration. And this is really based on the fact that our controller is running faster than our error convergence, right, which kind of rolls into that Lipschitz condition we talked about. And then thirdly, we can say that neural lander is robust to learning, right? And that's based on the stability analysis we've done. And we show that as the neural network performance degrades, right, we don't instantly crash or lose control of the vehicle. So we're really regulating the output of this black box model. So in the next section, we're going to talk about how do we extend neural lander to handle time varying disturbances. I'm going to pause really quickly to take a quick drink. I'll probably burn myself. Ouch. We'll go with a cold one. I did that just before the presentation too. Okay, that one's just going to wait till for later. All right, so let's go on to the next chapter. Oh, do you have a quick question? Stephen Lowe. Yeah, exactly. So there's a question in the chat right now. Does the fixed point iteration become a contraction under the spectral normalization? Yeah, that's exactly where that condition comes from. Are we connected? There we go. Okay. So now we're going to go on to neural fly, right? And now I have our next kind of key form of the dynamics for you, right? And now instead of our neural network being a function of X and U, right, where neural lander we were really focused on how do we handle the control input going into the neural network. Now I have this W, which is some unknown time varying. Here it's a wind condition. It could be really anything about the vehicle, but just some exogenous state that we don't measure. Right. Okay. So now we're on to the chapter for neural fly. Right. And this was a co-first software work with Huang and Shi. We both really worked together for the whole project. So first, I'm just going to give you an overview. We have this nice video, so I'm going to use it. So this will just be a quick overview of what we do in the project. It's running. Yeah, it's running. All right, so here you can see the real weather wind tunnel. And even though we're just trying to hover in place, right, we're just trying to demonstrate here that the wind has a significant effect on the vehicle. So what do? We're doing machine learning. First, we'll collect data by flying this randomized trajectory in front of the wind tunnel. You can see the vehicle pitching into the wind here. And we do that in 6 different wind speeds. It gives us a total of 12 minutes of data, right? So we're trying to be pretty data efficient here with how we train our models. And we're first going to learn a wind invariant representation of the aerodynamics of the vehicle. And then after we've learned, and that's using our training data, right? After we've learned that, we'll update that wind invariant representation through some wind-specific linear coefficients. And I say linear because that's easy to do in real time. And then here I just have some videos of the flight test we did. So our main test was this figure 8 trajectory. Here you can see it's one of the slower wind speeds, just so you can actually see the smoke without it just completely flying by. Here's kind of a fun long exposure shot we did of the drone flying the figure 8. And then a few stills just to show, you know, some of those. Right, you can kind of see that the aerodynamics change throughout different parts of the trajectory. So it's both a function of the wind and the direction the vehicle is headed. So here we're flying in time varying wind conditions, right? And you see we have the drone passing intentionally close to that gate, but it's able to react quickly enough not to hit it. And then this was what I thought the most impressive test, the one I thought might actually crash in real life. So it had all of that like 1 second to figure out what the wind condition is and correct for it sufficiently not to hit the gate before it went through. Here's a long exposure of that drone flight. And then we also tested this outdoors, right? We want to show that we're not tied to our lab equipment. So this is at the North Field. The gym is very gracious in letting us use the space, and they're very flexible. It's great. Yeah, so thank you for watching the video and sticking around for the first 20 minutes of my talk. But we still have a lot more to go. So what is the key idea of neural lander? I talked about it a little bit in the video, but we're trying to do this linear separation, right? So this is sort of, the motivation is similar to what you see in your partial differential equations class, right? We want to have a neural network that's a function of our state, the thing that we know. And then we want to have these, use my animations, right? And then we want to have these wind condition specific linear coefficients. Condition specific, so we change it for every new wind or operating condition. And linear means it's easier to update in real time. How do we develop a model like this? First, we need to learn our neural network. So we're going to use this idea called meta learning, which is that we want to learn a good representation. And then we're going to use adaptive control to guarantee stability in the closed loop control system while we're updating those linear coefficients, right? And I think that the core both of these ideas exist on their own. The core contribution of NeuralFly is how do we bridge the gap between them, right? And with adaptive control, we're trying to find a fast and robust adaptation algorithm for those linear coefficients. And for the meta learning algorithm, we're trying to find a good representation for all possible conditions. Okay, so let's talk a little bit more about that meta learning problem. So if we have, right, so this is, I think, the most basic learning problem where Y is the kind of data that we've collected. This is the aerodynamic force on the vehicle. X, again, is the state, right? So the neural network is a function of the state recorded throughout our tests. And then A is that wind-specific linear coefficient that we update for each wind condition. And so this neural network, right, again, shared across all conditions and the linear coefficients, we're going to be able to easily compute kind of in this framework. Actually, here it's just a least squares problem to find the optimal A in this case. This approach, though, has some drawbacks. First, it requires that we have IID, independent, identically distributed states, right? So that's, I think, a common assumption in machine learning is that the things that you say are random are actually random. It turns out that's not true for us. We're flying along trajectories, so you're not going to randomly jump, you know, every split second. And even we see that because we're flying in wind conditions, the drone, it needs to pitch into the wind to maintain its position. And so we see here, each color on this histogram plot is a different data set. So you can see 0 meters per second, 3.7, 6.1 was our maximum wind speed that we gathered data for. And you can see that the pitch angle for each of those tests shifts. So we have a kind of a domain shift problem. And when we first approached this, we tried this approach, and what we saw is that the shift led to overfitting, right? So it couldn't generalize well to new wind conditions, and it couldn't even really be updated well in real time. The neural network, that is. Okay, so slide 2 of meta learning. Let's make the equation more complicated. So what we've done here is now we add in this adversarial term, right? So H is an adversary, so you can think of it kind of like a game, where H is in our case, a neural network trying to predict the wing condition. And then the neural network now not only has to achieve that original task of getting a good prediction of the dynamics, but now it also has to remove this correlation to hinder the adversary, right? And so kind of the game that we set up here, it helps to remove the correlation in the data, prevent overfitting. And there is a trade-off. Essentially, we're throwing out the information that reveals the correlation, right? So we might be throwing out some pitch information, but it significantly improves the performance of the neural network. Right, so we reduce the overfitting due to the domain shift problem. Right, and then, so this is the setup for the problem. And in the paper, we have this, we call the algorithm domain adversarially invariant meta-learning, right? And the adversary structure plus the linear model of the neural network are kind of the key components of this learning algorithm. Okay, so let's go on. Right, so this is the same figure we saw in the video. So we've talked about how we get this wind invariant representation right here on the bottom of the figure. Next, let's talk about how we do this online update, the adaptive control component. So this hopefully will look a little bit familiar from earlier, right? We have some nominal control design in black, and then we have this neural network that we're trying to update in real time. So we have P is the neural network we trained offline, and then A hat is something that we're going to have to guess in real time. So we have this kind of long, messy looking adaptive control law that we've come up with for it. But if I break it down a little bit, right, this right here is actually just the form of a Kalman filter. So hopefully for a lot of people in the room, that's sort of intuitive on, right, if we set up a Kalman filter with the right equations, right, we can estimate these linear parameters in real time. And then we actually add in this tracking error term, which if you go through the proofs in the paper, right, you'll see that decouples some of the effects between the adaptive controller component and the controller component. Right, so again, we do stability analysis. Now we've added in the error in our estimation of those linear parameters to the Lyapunov-like function, right? And we have a similar result as before, where the ultimate error, the tracking error performance of the system, it scales linearly with the maximum error in now we call it representation error in the model. And then also the error in the system scales with how quickly the wing conditions are changing, right? So we're both robust to errors in the learning model, and we're robust to the change in wing conditions, right? Breaking one of those initial assumptions that we made when we were training the model. What are the key takeaways in NeuralFly? First, the Kalman filter kind of builds in regularization, and that's a key component of this algorithm because we can't guarantee what's called persistent excitation of the neural network, right? That's a classic idea or problem in adaptive control. And we've overcome it by saying, well, we can't do anything about it, so let's regularize it out. Using this kind of Kalman filter-like structure gives us fast adaptation, especially when we, for example, go from hover to suddenly flying or starting our figure 8 trajectory, right? We're ready to quickly adapt the new parameters that come up. And then also, like I mentioned before, that tracking error term makes this a composite adaptation law, which simplifies the stability analysis, decouples some of the gain tuning. All right, so let's look at some results. That was enough here. So first, we're going to look at a nonlinear baseline controller. Next, we're going to look at two what I think are kind of state-of-the-art methods, right? They have the best quadrotor control performance that I've seen in literature. And the underlying methods here are incremental nonlinear dynamic subversion and L1 adaptive control, right? And then we're going to compare that to our method NeuralFly. And all of these controllers are exactly the same, except for how they handle the unknown aerodynamic forces. So in the case of the nonlinear baseline controller, we have an integral error compensating for that disturbance force. In the case of the adaptive controller, I just wrote G hat, but we're trying to estimate the aerodynamics as a constant disturbance. And then NeuralFly, right, has this model that separates the dependence on the state and then those wind-specific linear coefficients. Okay, so this is the kind of key performance graph from the paper. So you can see that the blue line is NeuralFly, and we're outperforming that red baseline by up to 4 times. Right? And then we're not only that, we're also consistently outperforming these 2 other state-of-the-art control methods. And the way that NeuralFly does that, right, because they're all trying to estimate something online, is NeuralFly is incorporating that prior learned model or understanding of how the aerodynamics interact with the vehicle. So let's look a little bit more at that. So here I have the force prediction. This is in the Z direction, so up and down direction. So first we're going to look at the baseline controller. So this gray squiggly line is that actual online measurement of the aerodynamic force. And the red line is the integral error, which is compensating for it. So you can see there's a lot of lag, and it can't really quickly react to the changing aerodynamic force when we just have integral control. When we use the adaptive controller, right, the scheme with which it compensates for those aerodynamics is different, but it's still always reacting to the aerodynamic effects that are seen. So it's a little hard to see on this plot because of the squished axes, right? But there's always lag in compensating for the aerodynamic disturbances. For NeuralFly, these 2 are in our training data, and you can see that we pretty effectively anticipate the aerodynamic disturbance. And then even as we go to faster wind speeds outside the training domain, we're still doing a reasonable job of compensating for those disturbance forces. And now we have, right, these are those figure 8 trajectories that we flew for each of these methods. This isn't all of them. There's a few more in the paper if you want to see some more colored images. But we did a lot of flights, right? And what we see is that this red color indicates like almost centimeter level tracking precision of NeuralFly along most of the trajectory. And then, right, we're consistently outperforming the other methods and maintaining reasonable performance even at higher wind speeds. All right, right, we talked a little bit in the video about the outdoor flight experiments. So indoors, we flew with OptiTrack, the infrared motion tracking system that's in CAST. And a lot of times I get the question asked, well, you have these like almost perfect infrared tracking cameras. How do you know that your method really works? So in order to, I can convince myself pretty easily that what I'm doing works. But to convince everyone else, we flew it outside, right? We're using GPS for navigation here, GPS and IMU estimation. And you can see there is a slight degradation in performance, but that's just, I think, the nature of the fact that we have significantly lower knowledge of the actual position of the vehicle here. And then the final results I want to talk about is vehicle transfer. So we tested NeuralFly. We collected data using a different drone. So it's this little, this is what we tested on, right? We also had data from this little Intel Aero drone. And you can see here there's no propellers or anything, and that's because it died. So this is the corpse of a drone right here that we're seeing. So we had collected data because we were running all of these experiments. And then as hardware does, it stops working and you can't figure out why. This was discontinued at the time, so we couldn't really fly it or replace it. But we did have the training data, so it allowed us to kind of test what if we train the model with data collected on a different vehicle on our new drone. Right, and so that's this purple line here, right? And you can see that there's only a slight degradation in the performance, right? So that's that graceful failure. As we're going to a different vehicle that's configured differently, the model still performs reasonably well. All right, so that wraps up the NeuralFly section. So next we are going to go on to talk about how we are extending NeuralFly to fault-tolerant control applications. Take a quick drink of water. Chat. Okay, nothing in chat. All right, so neurofly for fault tolerance. So how do we learn to handle actuator failures in the system? Okay, so now I've written out the dynamics a little bit different yet again. This time I'm pulling out we're going to kind of explicitly consider how the control input interacts with the system and try to adapt to that also. Right, so this is our new unknown component. So neurofly for fault tolerance. So here you can see just an onboard view of one of our hex rotor drones flying in the lab. And so the test that we'll do, I'm actually going to show you, start out with a video of the performance here. So this is our baseline control method, right? And the drone is happily flying along. And then what we do is we kill one of the motors suddenly. And then we'll turn it back on, right? And so what we're trying to do is recover the performance of the vehicle even when one of these motors goes out. So the first question I think we should ask is, do we need to do anything different? Can neurofly already handle the actuator failures? So let's break down some of the assumptions that we had in neurofly and see what the limits are. So this is the same equation I showed you before, but now I've split up this tau and mu component. And in neural lander, we had this condition, right, this Lipschitz condition we talked about, that basically the neural network has to be doing less of the heavy lifting than the nominal model for the system, right? And that guaranteed the convergence of the fixed point iteration, allowed us to show stability. But then also, like I talked about, is as this expression approaches equality, or our fixed point iteration starts converging more slowly, right, the stability bound gets looser, because that was one of our denominator terms. So can neurofly handle actuator failures, right? Because it kind of inherits some of these assumptions from neural lander, or these results from neural lander, only by compensating for the actuator failure, right? So it can only try to cancel it out, and it's still reacting to that fixed point iteration dynamics. Right, and that happens because this B matrix is fixed, right? The only way that the neural network can compensate for the actuator failure is by like feeding through that fixed point iteration cycle. So what we're going to do is we're going to look at how we can extend our online learning framework to include the control actuation matrix, this B matrix, right? And then that's also going to present the challenge of now we have to update our control allocation matrix, or this B inverse term. All right. So first, let's talk about the second part of that. How do you design a new control allocation matrix? So if you have some force on the system that you want to produce this FD, right, you pass it through the control allocation matrix, which I wrote as, right, I defined B inverse as A on the last slide, right? And when you pass that through B hat, or your estimate of the underlying control actuation matrix, right, you want to get back the original force. The fact that we're flying an octorotor with 8 propellers means that we can't fully determine A is not fully determined from this equation alone. Although, okay, so what do we do? So the first thing we might try is to use a pseudo inverse, right? So remember, this is a lot like the least squares problem you see in linear algebra, right? But now it's just rearranged for matrices. So we have a right pseudo inverse of our control actuation matrix. This is good some of the time as a starting point, at least. The issue is that it doesn't account for input constraints. So especially when the vehicle tries to roll, it puts a lot more effort into, or a lot more of the control effort goes into the outer motors instead of the inner ones. And so this limits the control authority of the vehicle, which is especially important when the vehicle has a motor failure. So instead, we're going to use convex optimization to solve for a better control allocation matrix. The first thing we need to do to solve this optimization problem is we can rewrite this original assumption as a constraint on the A matrix, right? It's a linear constraint that this combined mapping has to be an identity. And then the actual optimization problem was really long and messy, so I abbreviated it here for you, right? So what we're going to do is we're going to find the allocation matrix that maximizes the control authority, maintains this this identity mapping, right? Or says that it's a good control allocation matrix for a system. And then we're also going to use some additional constraints to ensure that the motors aren't saturated, right? To maximize our control authority without saturating motors. Right. And this is a CAD model of the vehicle that we showed earlier, right? So we have 8 propellers, and we're going to test this algorithm on this vehicle when we know one of the failures. So I have another video for you here, right? So this is when we know the failures. As soon as this failure occurs, right there, the system, because we know the mechanism of the failure, right? We can tell the system the second it fails that it needs to reallocate and rebalance the system. And it's not a great frame to end on, but it does do significantly better in correcting. And I'll show that in some plots later. Sorry. All right, so, right, like I said, we're going through 4 different inboard motor failures is what we've shown so far and tested so far. So we've gone through those 8 inner motors, or sorry, 4 of the 8 motors. And we're going to represent the failures in our system by updating an efficiency value. So here you can see that plot. Each red region is a different motor failure. Here, when motor 2 fails, you can see that the efficiency drops all the way to 0 to say it's completely shut off. And then motor 4 fails, 5, and 7, right, which is just the numbering for the inner motors. Red region shows the motor failure, right? And then you can see on this plot, which is all the different elements of that control allocation matrix. It's a little bit of a mess and hard to interpret, but the thrust factor, roll, pitch, yaw factor, those are the columns of the control allocation matrix. So if you want to achieve some thrust, take the desired thrust times the thrust factor for the motor, and that tells you how fast to spin the motor. And you can see that as soon as the failure happens, because we have some, omniscient or true knowledge of the failure, right, we can instantly rebalance the system. So this is an idealistic, but ultimately unrealistic approach because we're kind of cheating by knowing the failure. But it demonstrates that the allocation works. So the next question is, how do we update the control actuation matrix, right? So what happens when you don't perfectly know the motor failures? So what we've been working on is this L1 regularized adaptation. This is an extension of the neural fly framework. So we're going to be updating these eta values, which are each of the motor efficiencies, and trying to estimate them in real time. And then we're also combining that with the neural fly framework so that we can handle other unmodeled disturbance effects. I have a nice big long equation here for you, right? But the idea is the same as what we had before. First, we're going to try to minimize the prediction error, right? So y is the measured aerodynamic force. And then we're going to try to get the things that we're estimating online. We want them to match the measured forces on the system. So we're going to be minimizing this cost. And then the L1 regularized component here is this regularization term on the motor efficiencies. So this is, right, in computer science, you might know this as like lasso regularization, right? But using the one norm allows us to find a sparse set of failures, right? So it tries to only choose a couple motors that failed to describe what's happening rather than tweaking all of the values. But it introduces a lot of challenges for showing the stability of the closed loop control system. So the way that we're going about this is we have this, again, Lyapunov-like function. It's very similar in structure to what we had previously. The first kind of key step is to figure out how to rearrange the dynamics so that the error, right, it's because this efficiency is a multiplicative term, we first have to figure out how to kind of pull it out of the equation or make it an additive term, right? And then, sorry, I'm gonna look this way. Right, so we have an additional challenge here, which is because there's no closed form solution for this lasso regularization problem, it's difficult to show the stability of this. Oh, I thought I had another bullet point. So what we're going to do is, what we're doing in the paper is using a smooth approximation to get a closed form solution. And we're also playing around with some other ways to show stability for this adaptive control law. Okay, so let's look at another video of the performance here. Same inboard motor failure. My timing is a little different on each video. Right, and you can see again, we freeze the motor and we're able to recover almost instantly. Okay, so what does the performance look like? We saw those videos. None of them crashed, you might notice. So we're going to say, are any of them really that much better? Oh, sorry, we're going to look at the lasso regularization first. So performance and flight tests. Okay, so on that outdoor flight test, right, you can see I've broken up the chart a little bit so you can more easily see what's going on. So the red regions are each of the motors that failed. And you can see that because we're using that L1 regularization, right, we are predominantly blaming the one failed motor for the failure. There's obviously still a little bit of work to do, and this is a work in progress, right, because of this kind of confusion that happens here near the end. But part of that is also that because we're running these tests back to back, there's still a little bit of remembering the previous failure. Right, so what I think is cool about this is that the instant the failure happens, right, we're able to recognize that on the system and compensate for it. Right, and this is like, again, squished axes, but this really dives right down, and in less than a second, you identify the failure and rebalance the system. All right, okay, now we're going to look at the performance comparison. So the baseline method, which does not reallocate the controller, it recovers like we saw, but the recovery takes several seconds, right? And this is the most benign failure that we're looking at. It's an inboard motor. It's a very over-controlled system. And we're only hovering, right? We haven't yet started doing the test where we're tracking a trajectory or kind of mid-mission and this motor failure happens. So the L1 regularized adaptation, right? The motor fails, and then we're able to very quickly recover the performance of the system. And then something that I was kind of surprised about was that we actually even performed better than the known failure case. And the reason that the known failure case isn't perfect is because when you need to rebalance the system, right, you totally lose one motor. You need to have other motors spin up to react and kind of compensate for the lost motor. So this transient is that kind of like motor spin up time that we're seeing as we recover from the failure. All right, so yeah, so that's work that we're doing to extend neural fly for fault tolerant control. And now we'll go into the last section, which will hopefully be brief since we're running low on time. And we'll talk about kind of what I hinted at there with the, delayed response of the motors. We'll talk about some ways that we've looked at to correct for that sort of behavior. And we're going to do that by explicitly considering time delays. So I wrote out one form of time delay here. So if the control input u at time t, right, is what you want to apply, you actually are applying something that you came up with delta seconds ago, maybe 100 milliseconds ago, maybe 10 milliseconds ago. Oh, I have a box. All right, so delay compensation. So what are the sources of delay that we'll consider? First, we're going to look at actuator response time delay. So one example of this is the attitude control is faster than the position control. So if you look at this image of our quadrotor flying out at Northfield, right, this is the direction that the vehicle is pointing and the direction that it's producing thrust. But suppose that to maintain your position, you want to produce thrust in this direction, right? It's going to take the vehicle some time to, right, correct the attitude and track the command that you give it. And then also, like we had in the fault tolerant control case, right, the motor response time will also factor in here. And then, like I talked about on the last slide, we have some dead time communication delay. So on this system, with some CERF students, I actually tried to quantify and study the amount of delay that we have in our system. We found it's around 30 milliseconds. which is at the point where it starts becoming significant for the vehicle. Right, so how are we testing this algorithm? We're testing it in this this Python-based simulator, right? So it's a physics engine that I developed. Physics engine saying an integration, an RK4 integration of a dynamic scheme, right? And it incorporates effects that we're trying to study the effect of, such as the discrete control updates, motor delays, and then also these unknown aerodynamics and forces. I integrate at 1 millisecond time steps using RK4. So this is something that I found that, right, we're integrating it fast enough that basically integrating faster gives us no improvement. So, and then we're testing some of the discrete effects of the controller. We have analytic motor dynamics. That's something that runs very fast on the real system. But our angular rate control, attitude control, and position control all run slower than, than the dynamics of the vehicle. So what is the method here? Right, it's first order delay compensation. So first order should give away a hint here. So we're looking at, right, so this is what I described on the last slide, now written in math, right? So we're not actually applying the control input U to the vehicle, but some delayed by time delta value that's also passed through these low pass filter dynamics, resulting in a delay in our control input. The method, as we've studied it so far, it works with any control design. So for example, we can consider the neural lander control framework. And what we're going to do, first order, right? So we take the derivative of the control input. Oh, whoops, there's supposed to be a U dot term here that it has disappeared on me. So what we do is we take the original control input and we add some constant times an estimate of the derivative of the control input. And what that does is improves the performance in the presence of these types of delays that we're looking at. So on the bottom here is our baseline control method, right? And you can see that we get, right, 0 is the lightest color on the plot. You can see that with no computer delay, none of that transit time of communication, and then no motor dynamics, you can see that we get almost perfect tracking, right? Our tracking error is very close to 0. But then as both of these delays increase, you can see the tracking error gets worse and worse. Using this first order delay compensation method, you can see kind of in this region we're interested in, right, less than 50 millisecond delay. This is kind of the motor dynamics range we're looking at. You can see we maintain performance. And then we actually have to get all the way up to a 200 millisecond delay before the vehicle or the simulated vehicle crashes. Right. So, and the reason this works is because this is a first order, right? First order in the Taylor series sense of the word. It's a first order approximation of the exact or perfect way to compensate for the delay. Right, and the way we formulate it is that it's general for any underlying control scheme, so we can merge it with all of the learning-based control frameworks we've talked about so far. All right, so what have we talked about? We talked about neural lander, some fundamentals for incorporating residual learning in our control scheme. Neural fly, how do we extend that when now the environment around us is changing? Neural fly for fault tolerance, right? Can we extend it to handle actuator failures or more significant effects on the vehicle? And then I've also talked a little bit about delay compensation, right? How do we, this is something that the neural network, because of the way we set up the problem, can't learn. So can we compensate for it in a different way? There are lots of equations to describe how we do this. And so have we addressed what challenges kind of were we setting out to address, and have we addressed them? So first, we've looked at robustness to challenging conditions, right? So we talked about results flying in the wind tunnel, where we have this nice uniform wind condition, but we're also robust to changing wind conditions, which is one of the experiments that we did in the lab. Right, we've worked with different vehicle designs, and something kind of an interesting future direction is to actually apply it on some of these vehicles with these large wing-like surfaces sticking out from them. And then, right, even consider applying it to larger scale vehicles. And then finally, right, we've talked about some ways to build on neural lander, neural fly, right, the learning-based control schemes to enable more fault-tolerant control. All right, so we're kind of getting to the end. So I'm going to list out the publications we talked about here. And thank you all for attending. I'll do a few thank yous. So thank you, Sundro, to my advisor. Thank you to all my committee members for taking the time to give me feedback. Right, I have a ton of co-authors and collaborators. Thank you to all of them. My lab group has been great and supportive. Monday, I was like, oh, by the way, I would like to do a practice presentation. And they're all like, sure, we're available for that. A lot of my GALSIC cohort is here, right? And we went through a gauntlet of coursework together, and they've been a great source of support. Right, I work with a lot of industry collaborators and grant sponsors, and that's been great. Michelle Judd, who has been featured in this audience in photo form. And the Keck Institute for Space Studies, right, have been a great source of support on campus, as have the Caltech Alpine Club, the Wind Orchestra, and just a ton of other groups at Caltech that make it a great place to be. Finally, we have a huge Zoom audience. There's 28 people in the Zoom right now. A lot of friends and family who are able to come out and support. So appreciate all of it. So thank you all. Mhm. Right. Yeah, I think that's an interesting question. And the way that we've set up the controller, just like the time delay is kind of orthogonal to the component that we're trying to model with machine learning, right? Sensor failure, we're intentionally not compensating for that. And that's one of the ways we get robustness. So for something like a minor sensor failure, right, we'll try to get good performance as the sensors see it. But to look at total loss of a sensor or like bad or malignant data, that's kind of that you're right, that's a different direction of research that we don't directly address here. We'll keep fighting to do what the sensors tell us is happening. So yeah, thank you for the question. Sorry, could you say that one more time? Mm-hmm. Yeah, that's a great question. So I think there's a lot of potential there. We're sort of limited. So the real weather wind tunnel and cast, right? We were only testing uniform flows, and it's like its whole own area of study to understand how to generate wake-like flows and stuff like that off the wind tunnel. So we didn't really want to touch that. So we just sped it up and slowed it down. So we had that time varying wind, which shows some robustness to these kind of effects. But I think especially when we're looking at like the urban canyon or wakes behind a building, right? There's additional structure that you might hope to learn in those cases, yeah. So we didn't really look at rope or structured time varying disturbances, but just robustness to time varying disturbances. Yeah.
So I was doing company
Mhm. Yeah, that's a great question. So we are looking at over-actuated vehicles, right? So, right, cases where losing one motor failure, the number of things you can control, right? Like the 3 directions of your attitude or orientation, right? Your height, you can still control all of those things. The ways that you have to address, for example, a motor loss on a quad rotor is a little bit different in nature. So you have to, right? So on a quad rotor, you have 4 control inputs and 4 degrees of freedom you're trying to control. So if you lose a motor, you have to basically give up on one of your degrees of control. And so that becomes a little bit of a different problem because now it's like, which degree can you afford to give up? Or, can you plan a trajectory that doesn't need that to reliably land or safely land? So that is both, that's not exactly something we're trying to target, right? Because just by nature of the difference between those problems. Yeah. Yeah. More than 10. Okay, so at one point, actually, it's not in the slide deck, but I had a picture of all of the broken propellers from, where is it? From the Neural Lander drone, that Intel Aero drone. I had at least a dozen broken propellers that I had saved. So, and most of the time, the propellers don't break when you crash. So, yeah. I've been checking. I don't think so. Have you seen any come through, Josh?
In the front orange, we are looking at the motor phase.
Mm-hmm.
So, for example, I observed the sit on a wall. This is the algorithm from the output that
Mm-hmm. Yeah, that's a great question. So that's why we're looking at kind of a motor failure framework that is compatible with those learned dynamics we had earlier. So something like a bird landing on your vehicle that changes your center of mass, right? That would be come into play more in something that learning-based term, or even just like a straight up, L1 style adaptive control term could compensate for. So yes, we're handling it by kind of looking at both those frameworks together. Mm-hmm. All right. Thank you for joining, everyone. Not sure if you could hear Yisong, but I'll be switching off Zoom for the closed committee session.